Mic check, 1 2, 1 1 2, mic check, mic check. Good evening, everyone. Welcome to another episode of Physics Rocks It's True. Tonight we are looking at electricity and two-way switching. Domestic electricity, so we're moving away from our circuit theory and into the actual real-world application. Now, the key thing about electricity is that you've made it, it's a commodity, you own it, and you want to sell it. Okay, that's if you're a big electricity supplier somewhere in the world. The problem with that is you need to know how much it costs, and more importantly, you need to know how much people are using. So that's simple. Electricity is a type of energy, it's electrical energy. So the equation is the same as any energy equation, that energy is equal to, in general, in all of physics, it doesn't matter what branch you're using, energy is equal to power multiplied by time. Okay, now in electricity we generally have this as P equals I, or E equals IV T. Okay, that IV is the power bit, T is the time bit, and then we rearrange it to ITV, like we did in our last one, to make it a little bit more memorable if you're actually sitting in the kind of UK and Ireland, you know what ITV is. But we're not going to do that tonight. We're not going to do that tonight. We're just going to stay with energy is power times time. Now, broadly speaking, energy should be measured in joules, power should be measured in watts, and time should be measured in seconds. These are our SI units. These are our proper units to use for this. The issue comes when we're using these in the home. Okay, when we're using these at a kind of industrial level, it becomes a problem. It's fine at lab level, but it's not so much a good idea at large levels. Now here's why. Let's imagine I have a 20-watt light bulb. Okay, so standard energy saving light bulb, not super efficient, but pretty good. Okay, so we've got a 20-watt light bulb, and we run it for let's say an hour, 1 hour. All right, so 20 watt light bulb running for 1 hour. Now let's do the calculation of that then. Energy equals power multiplied by time, and this is our kind of key equation that we want to go here. Energy is equal to the power, which is 20, multiplied by the time. That has to be in seconds. So 1 hour, 60 minutes, 60 seconds in every minute. That's 3,600 seconds. Okay, so that gives us an energy equal to 72000. Okay, so 72,000 joules from one light bulb in 1 hour. Now think about scaling that up. If that's a light bulb, and that's energy efficient. Think about when you're running a shower at a couple of kilowatts, when you're running a kettle, when you're running your immersion heater that heats vast quantities of water, when you're running all the bulbs in your house, when you're running your 500 watt power supply for your computer and you're running it all day and all night, downloading all those videos and torrenting all those things. Not that you would, because that's illegal. This number rapidly becomes very, very, very large. And if I said to you, in a day, you could use, let's give you a ballpark. Let's give you 80, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's say we give you that many. Okay, so that'd be 800 million. So this is about 80 billion joules of energy in a day. Do you think that's a reasonable number based on the fact that 1 hour you're using 72,000 joules for a light bulb? Depends on how big your house is, depends on how much energy you use. The problem is you actually don't know the answer to that question off the top of your head. You think that number looks very big, but then you think the other number looks pretty big too. So yeah, big numbers happen, but that seems really big. Maybe it's not that. And that's the issue you run into if you're using the joule. More importantly, if I want to run a light bulb for an hour, how much would you expect to pay for it? Okay, would you expect to pay a penny? Does that seem like a good deal? Does 2 pence seem like a good deal? 2p for an hour, that's not bad. 3 pence for an hour, 4 pence. Now, you might think 4 pence for an hour is expensive, you might think 3 pence for an hour is expensive, 2 pence or what, but you're going up in multiples here. Alright, you're going up, like 1p to 2p doesn't seem like a lot, but it's a 100% increase. Right? From 1 to 3 pence, you're tripling the cost, and it doesn't seem like anything. So you can be absolutely hoodwinked here. You can be absolutely done in by a per joule price. Because if I told you, let's say I went for the absolute maximum of 4p for an hour, which is probably quite expensive, right? That would be 4 pence divided by, let's see how many joules. That would be 72,000 joules. Okay, divide it by 4 to get the price per penny, or how many joules can I get for a penny? So again, we'll grab our calculator from the side here, calculator, bring that into screen. 72,000 divided by 4. If I told you you were getting 18,000 joules for a penny, that sounds quite good. Yep. That seems quite good, doesn't it? 18,000 of anything seems quite good. And you know that a joule is roughly the energy taken to lift an apple a metre. So lifting an apple 18,000 metres seems pretty impressive. But it's not, and you're being ripped off. And this is the problem. Human beings are bad at big numbers, and we're bad at small numbers. So what we need to do is we need to develop a system that doesn't do this, that doesn't have us dealing with stupidly large numbers where we don't know if that's good, bad, or indifferent. That we're not dealing with things in pennies. Do you always get money in pennies? I see in the chat there. That's the problem, isn't it? That if you're dealing with this type of thing, you're not just dealing with pennies, you're dealing with parts of a penny. You're dealing with thousandths of a penny. And we don't want to do that. We don't want to do that. We want to deal with sensible things that we can get our heads around. So we do this. We do energy equals power multiplied by time. Okay, we can't get away from that. That's the fundamental basics of physics. Okay, so whatever we come up with has to adhere to that. And if you're following along on the in the question sheet at home, this is what we're talking about in the second question. That this is still scientific. We have to keep it scientifically valid. It has to be some form of measurement of energy is equal to the power multiplied by the time. But we're not constrained to watts. That's a convention. That's a convention, constraining it for watts. So what we're going to do here is we're just going to measure our energy in kilowatts. Right, it's kind of the same. Okay, we're just factoring it up by a scale of 1,000. And instead of having our time in seconds, we're going to put our time in hours, which I'll abbreviate to HRS. Okay, so fundamentally we haven't changed the math, we've just changed the scale of the numbers that's going in. Okay, so let's do our light bulb calculation again. Okay, we'll grab our calculator just to show you what's going on. That's 20 watts, but in kilowatts we divide that down by 1,000 to get us 0.02. 0.02. And remember we said we had it running for 1 hour, so that's times 1. So the energy I'm using is equal to 0.02. And automatically that looks like quite a small number, which is what we'd expect because light bulbs are not big energy items. So we're in the right scale. 0.02 is a small number, but it's a number we can get our heads around. But it's not joules. Now, this is not joules, because joules require our power to be in watts and our time to be in hours. And it's not that. This is some form of new unit. And helpfully, the unit is simply the combination of these two, that it's 0.02 kilowatt hours. Okay, and that's sometimes separated with a space, but you can put it together. Notice there's no slash, it's not kilowatts per hour because it's multiplying. This is just like algebra. You've got letters, stick them together when you're multiplying. This is kilowatt hours. KWHRS. And this is a unit of energy, which messes a pile of you up. And there'll be a question somewhere in your GCSE exam that says, you know, what is this a measurement of? And this is a measurement of energy. Even though you think watts is power, it's power times time, so this is an energy. All right. Now, there must have been a marketing decision made at some stage that this thing here, which is called the kilowatt hour, so KILOWATT, kilowatt hour, looked a little bit too sciencey, as if we were hoodwinking people. So they had to come up with a different thing to call this. So we now call, you will occasionally see this referred to as the unit. Meme fans, this is the absolute unit of domestic electricity. All right. Thank you for the comment there. Dark platinum graphs with 4 squares or not. Dumb graphs with 4 squares. Test your mathematical ability. So 0.02 kilowatt hours. This is called the kilowatt hour, but it is also called the unit of electricity. So when you're talking about electricity, you tend to talk about the units you use. All right. So that's how you calculate it. That's how you calculate it. No, so that's how much you use. All we do is work out how many kilowatts you're using, how long you've been using it for, add it all up. That's your total energy. We still need to charge you for it. Remember, that was the whole point of this back at the start. So how do we charge you for it? Well, charging you for it is done exactly the same as charging you for anything in life, right? That the total cost equals the cost for one thing multiplied by how many you bought. All right, so if a bottle of Coke costs £1.50, right, and you bought 2 of them, you spent £3. You bought 3 of them, you spent what, £4.50. You bought 4 of them, you spent £6. You bought 5 of them, you've probably got diabetes. Okay, so in terms of total cost, just the cost for one of them multiplied by how many you bought. For electricity, the total cost is equal to the cost for 1 unit multiplied by how many units were used. Easy peasy. This is not an official equation, but I'd learn it as if it was. Just a handy little thing to know. Write that down, impress your examiner, let them know what you're thinking as you're going through it. Learn that. Okay? Happy? £1.35 apparently for a bottle of Coke. Is that Diet Coke, with no sugar, or is that proper Coke that's going to mess you up inside? Okay, so on we go. On we go. How does that work in real life? Well, what you tend to get is in actual real life. This is one of those very few things that you learn in school that will help you in your life. You will at some stage get an electric bill. You may get it every month, you may get it online, you may get it every 3 months, you may use a meter, you may use all sorts of things. But broadly speaking, it breaks down into a few basic parts. Okay, the first part is that you have a meter reading that you used to have. So let's say 15862. Right, and what that is that's the number of kilowatt hours that have been used in your house since that meter was installed. Okay, may not be since you moved in, but since that was actually installed. The second one on your bill will be the meter reading when the man came around, or the woman, came around to read your meter. They've been chased by your dog, they've been through hell to get that, and the new reading is here. Okay, so this is your previous reading. We'll pop this in. This is your previous reading. It's the last time they came. It was this. And then this is your current reading, which is this. Alright, so you can just do a bit of subtraction to work out how many units you used, and we'll do that. We'll do 17352, take away 15862, and we've used 1490 units. So we used 1490 units. And there's some fancy bills will tell you what you did per day and all sorts of things, but that's fine. Over here then, you'll get the price per unit, or kilowatt hour, depending on how fancy your company are, as to whether or not they call it a kilowatt or a kilowatt hour, or whether they call it a unit. Doesn't make any difference, it's the same thing. Right, now in here will be some vaguely normal number, like 15 pence. Okay, that's not a bad deal actually, 15p per kilowatt hour. Jump at that. And then down here then we have total cost. Right, so grab the calculator, and we've got 1490 multiplied by 15p is 22,350 pence. Now we probably don't want it in that. We'll divide that by 100 to get our answer in pounds, and that's £223.50. 223.50. Okay, that's a number you can get your head around. That if your bill suddenly goes up by 20 quid, you go, hey, wait a minute, we're 10% up, what's going on? If it goes down by £30, you're like, oh, happy days, we're making good savings here. You're not dealing with silly numbers, you're dealing with numbers that you can deal with. And if that turns up every 3 months, you're probably reasonably happy and living by yourself. Oh, pardon me. Flicked across the wrong thing there. Okay. That's what we're after. That's all there is to it. Now, questions basically revolve the way around up. You will get this, this, and this, and be asked to find the total. Or you'll be given the price per kilowatt hour, the total, and being asked to find like maybe one of the previous meter readings or the units used. You'll be given most of these and asked to find the missing one. That's the deal. Okay? So that's that. Easy. Easy. So on to our next thing, which is two-way switching. Okay, so paying for electricity, that's your equation there, and understand that it's the kilowatt hour, which is simply a rearrangement of energy equals power times time. So switching. Right, so switching comes in essentially two forms at GCSE. You have one-way switches and you have two-way switches. Yes, you get three-way switches, four-way switches, five-way switches. All of these things exist, but as far as our course is concerned, we're only concerned with one- and two-way switching. So let's get ourselves a little power supply. In fact, let's do it. Let's do it a little bit more fun. We'll do it as sort of mains power supply. You probably haven't met this yet. If you haven't started doing AC and DC electricity yet, which we haven't on this channel, but you might have at school, then you probably don't recognize this yet. But we'll get to it. Okay, and let's build ourselves a little circuit. Okay, so I need to get myself just do a simple one with a light bulb. Okay, so grab a little bulby thing. Spare no expense in the graphics design here, really. You can see that my art skills are entirely done on the thumbnails. I'll try and leech you into the place. Go check out the graphics quality, and then once you've been watching for a few minutes, you think, I'm going to miss something, so I can drop the quality horrendously. Right, so basically this is a power supply here. And this tends to be what mains power supplies tend to be drawn like. They get a little symbol in here that's like a wave, because it is a wave, like that, which is usually a little bit smaller. It's not an N, it's a wave. It's an uppy downy wave to show that the power's moving. But whatever. Okay, so we're going to supply this. Now all we have to do, let's say that this is like our positive side, this is our negative side, or whatever, it doesn't really matter. What we need to do is we need to develop a switch system that turns this light bulb on and off. Right, and there's nothing to that. There's nothing to that. All we do is grab ourselves a switch and pop it in here. So we need a switchy thing like that. We need a bit of extra wire. Goes like that. And that'll do, but we want to be a wee bit fancy, so we'll put some little dots in. little circles where the connections are, because it just makes it look prettier. And pretty matters in exams, believe it or not. You know, examiners are human beings too. So if you look like you know what you're doing, you tend to get away with a few more mistakes. Don't tell them I said that. It's a thing. Okay, so that's your power supply. When the switch is open, the light bulb is off. When the switch is closed, the light bulb is on. And we have to make an effort, so on. Cracking. And then when the switch is open, it's off. See what I did there? See what I did there? Cunning use of the undo tool. But that's no use if I want to switch the light on and off from different locations. And that's where two-way switching comes in. Now the automatic knee-jerk reaction here is to go, well, if you want to switch it on and off from two locations, let's just stick another switch over here. Okay, so we'll break this wire in half and we'll basically just copy and drop this switch over. Let's do that. Right. Job done, let's go home and eat some cake. But this doesn't work. Obviously it doesn't work, because when I close this switch, well, electricity can, this is looking good, it's looking good, right, we don't have a complete circuit, so we've got nothing. Okay, so when I close that switch, I can't do anything, but I can come down here, yeah, and I can close that switch, and absolutely this will light up. We've got a complete circuit going on, and when I open either of these switches, it'll go off. But that's not what we want to happen. What I want to happen is when I switch either of the switches, the light does the opposite of what it's doing now. And what I mean by that is this light is currently off. I want to be able to press either switch and have the light come on. And if I press this switch, yep, that's great. That works. But if I press this switch, it stays off. So it doesn't fulfill our criteria. So what we need to do is we need to build a system that does meet our criteria. And it's one of those things that once you see it, it seems really easy, but good luck actually coming up with this on the fly. This is one of my favorite bits of electricity. What we do is we put our bulb somewhere on the circuit that's on the main branch. Okay, so anywhere over there is good. Okay, and then we have a wire coming out of it. So if electricity gets to this stage, it's definitely going through my bulb. But the key bit here is that my electricity needs to have a couple of parallel choices. Okay, the parallel bit here is really, really, really important, because that's what makes it. Okay, so what we do is we have two parallel lines here. One wire here, not connected to anything. And then we have another one that comes off here and reconnects up with this. Oh, that's dreadful. We'll be getting complaints. Yeah, that's a bit better. Oh, try again. Okay, so what we do is we put a switch that moves to one of two positions. So rather than just being in the on-off position, it has an up position and a down position. I'm going to copy and paste these because it's going to really annoy me if they're not the same size. So drop that there and pop that there. Okay, so rather than have just it can be in one position or hanging up in the air, my choices are my switch can be in one of two positions. It can either be connected to this position or this position. It can't be in between, it can't be floating about in the air. It's either here or here. Alright, I'm going to actually draw these in red so that we can follow this a little bit better. So that one goes there, and let's put this one here. It's not the best drawn, so let's just shorten these up a bit so that they actually look like they're switches and they're doing what they're meant to be doing. What the heck was that? Apologies for the really bad drawing this evening. That's a bit better. This is what you get when you do live. See, if we had editing would help. Any professional editors out there want to help me out, that's great. Right, anyway, there we go, two switches. So in this situation, this is great. This is absolutely wonderful. Our electricity is going to come out. It's going to travel around to here. It's going to find its way to the switch and goes, yep, we'll go that way, and then we'll go that way, and then we'll go that way, and then we'll go that way. We'll come up around here, and our light will be on because we've got a complete circuit, and this is amazing. Now, the cool bit here is no matter which switch I flick, if I flick this switch, that stops being true. Notice I go here, I go here, I go here, and nope, no way around. But let's imagine that I'd done the opposite. Let's imagine that instead of flicking that switch, I flicked this switch. And again, I end up in a situation where I get around here, 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 and I end up dead-ended. And it doesn't matter which side I go from. Okay, I go from this side, this side, this side. It's still a broken circuit. Okay, so I have no way around that, and this is what a two-way switch does. It allows switches that have two positions at either end, and as a result of having two positions at either end and some parallel lines between them. The parallel lines are important, that no matter what position you press, you're going to end up doing the opposite to your light bulb as to what it was already doing. This is a two-way switch, and this can be adapted for upstairs, downstairs. So this would be like a hall switch, upstairs, downstairs switch, just as easy. Just take the whole thing and rotate it. So grab that, and there you go. You've got the stairs in your house. Okay, bring this switch to the bottom of the stairs. And apologies for that. That's all right. That's fine. There's a switch at the bottom of the stairs. I'll bring this switch to the top of the stairs. So move this up here, and we'll shorten that one. There we go. Looking lovely. And that's it. Okay, it doesn't matter where I put my power supply. I can put my power supply over here, over here, over here. All that has to happen is power supply, one side goes to one end of the switch, the other side goes to the bulb and the other end of the switches, and you're in business. And equally, I could have put the bulb like over here. That would have been fine as well. It would have worked exactly the same way. I would have had this, obviously, a complete circuit there, but it doesn't matter. If the bulb's in there, same thing works. All right, folks. So these are, in terms of examples and questions, this is pretty much all you get. All you get for these questions tends to be either fill in the missing units here, or you end up with part of this drawn for you. Usually you get something that looks a bit like this, and then you go, right, okay, let's actually do this rather than talking the hypothetical. So let's grab our bulb here, and we'll fill it in white so it's not, because we shouldn't be able to see through it. And send that backwards. Order, send to back. There we go. What tends to happen in exams is you get that. You go, I want an upstairs, downstairs switch. I need a switch at the top of the stairs in this position. I need a switch at the bottom of the stairs in this position. Go do it. How do I do it? And how you approach these questions is dead simple. I need two parallel lines between my switch positions. That's it. Okay, so draw two circles, one circle at switch position 1, one circle at switch position 2, and draw two parallel lines between them. And then stick circles on the end of those parallel lines. Like that. And then draw your switch. And it doesn't matter which position you draw your switch in, just make sure it comes from switch position to connection. And there we go. And that's in the off position. And if you flick either of them, it's on. Job done. Easy peasy. Alright folks, thank you so much for tuning in. That you've been a good chat this evening, considering that you all did your exam today if you're watching this live. So I really appreciate it. If you're not subscribed, I'm at 398 subscribers. I need two more. I need two more for the kind of number file in me to be happy. Okay, I might even do a face reveal, you never know. Alright, so thank you for your attendance. Remember, in the links below in the description, there is a worksheet. If you are not doing anything else, grab that worksheet, have a little try at it. It certainly helps to reinforce the learning that you've done here this evening. And I will see you next time. So all that is left for me to say is, don't forget, people, physics rocks. It's true.